Porphyry copper deposit. Definition: Porphyry copper deposits are large tonnage, low to medium grade deposits in which primary hypogene or minerals are spatially and genetically related to felsic to intermediate porphyritic intrusions. The ore is dominantly structurally controlled. The deposits are magmatic hydrothermal with the sulfide and oxide minerals precipitated from the saline aqueous solutions at elevated temperature. They get their name from the porphyritic texture of the plug-like intrusions and the dikes spatially associated with the mineralization. Multiphase intrusions are typical, and one of these usually has an aplitic texture, sugary groundmass. The ore occurs in narrow, closely spaced veins, hydrofractures, within hydrothermally altered rock. This produces stonework ore and what has been called disseminated ore, which is actually mineralization along numerous closely spaced microfractures. To be mineable, these deposits must be amenable to bulk mining methods. Geographical distribution. Porphyry copper deposits occur throughout the world in a series of extensive, relatively narrow and linear metallogenic provinces. They are predominantly associated with Mesozoic to Cenozoic orogenic belts in western North and South America and around the western margin of the Pacific Ocean. They also occur to a lesser extent in the Tethyan orogenic belt in Eastern Europe and in Southern Asia, as well as in Paleozoic orogens in Central Asia and Eastern North America. Their district's location may be controlled by major regional faults such as the Rio Grande Rift in the southwestern United States. This global distribution of porphyry copper deposits is a function of the uneven distribution of magmatism through geological time, which is directly related to plate tectonics and plate configurations. The dominance of Phanerozoic, Cenozoic, and Mesozoic deposits over those in older terrains is mostly due to preservation and exposure. Porphyry deposits form relatively near the surface, typically 1 to 4 kilometers depth, and are subject to subsequent tectonism, erosion, and/or barrier. Tectonic setting. Porphyry copper deposits occur in a variety of tectonic settings and typically represent root zones or bottoms of stratovolcanoes and/or calderas in subduction-related continental and island arc settings. Stratovolcanoes. What are stratovolcanoes? These have relatively steep sides and are more cone-shaped than shield volcanoes. What are calderas? It is a large depression formed when a volcano erupts and collapses. What are island arcs? They are chains of volcanoes that are caused by partial melting of the plate at a subduction zone because of typically groundmass convex towards the ocean basin and a trench. They are said to be island arcs. In the southwestern United States, porphyry copper deposits are associated with granitic rocks emplaced in a continental setting, within or along the margins of calderas that are now largely eroded. In modern island arcs that border the Pacific Ocean and along the continental arc that is associated with the Andes Mountains, the deposits are related to both andesitic stratovolcanoes and calderas. Porphyric copper gold deposits, such as those associated with Triassic and Lower Jurassic alkali intrusive and volcanic rocks in British Columbia, formed in an island arc setting. Although possibly during periods of extension, porphyric copper deposits in the Yulong belt of Tibet are related to pull-apart basins in a large post-subduction strike-slip fault. Size and grade. Porphyric copper deposits are large and typically contain hundreds of millions of tons of ore. They do range in size from tens of millions to billions of tons. Copper grades are highly variable, ranging from 0.2 to more than 1.6%. They average about 1%. Other common economic metals associated with the deposits include molybdenum, 0.005 to about 0.03%, gold 0.004 to 0.35 gram per ton, and silver 0.2 to 5 gram per ton. Average deposit size is 750 million tons at a copper grade of 0.75%, with low grades 0.2 greater than 1%. What makes these deposits profitable is their very large size and their shape. Ore minerals. Chalcopyrite is the main ore mined, often with minor bornite and chalcocite. Molybdenite is commonly present, and other minor minerals are energite, tetrahedrite, tennantite, electrum, and cassiterite. The main gangue sulfide mineral is pyrite, and magnetite is the main oxide mineral. Secondary or supergene minerals associated with porphyric copper deposits are chalcocite, coelite, cuprite, chrysocolla, azurite, and malachite. Hydrothermal alteration and zoning. Hydrothermal alteration is defined as the chemical and mineralogical changes in rocks brought about by warm to hot aqueous fluids circulating or passing through those rocks. The fluid-rock interaction causes chemical and mineralogical changes in the rock as well as changes in the fluid composition. Such changes depend on: number one, the time and duration of the interaction; number two, the permeability of the rocks. Alteration will be more intense along more permeable zones. Number three, the composition of the fluid, acidic, basic, or neutral. Number four, the temperature of the fluids. Alteration is studied by: number one, economic petrology, looking at alteration minerals and assemblages present in the rocks and comparing them to unaltered rocks. This is done via hand samples, thin sections, and mineral chemical studies. Number two, lithogeochemical studies looking at chemical changes that have occurred in the altered rock relative to an unaltered equivalent rock. In porphyry deposits, hydrothermal alteration is word separate and is typically zoomed on a deposit scale, as well as around individual veins and fractures. Alteration zoning can be defined by distinct mineral assemblages. Typically, the upper portion of the host intrusions become extensively fractured due to a. Adjustment of the adjacent country rocks as the intrusion cools. B. High vapor pressure of the fluid, fast boiling and volume increase. These fractures are permeable zones along which the ore fluids migrate both laterally and vertically. Alteration zoning in porphyry copper deposits is based on: number one, lateral and vertical movement of the hydrothermal fluid; number two, Cooling of the hydrothermal fluid as it moves upwards and outwards, accompanied by a possible decrease in pressure. Number 3, degree of interaction with groundwater. This leads to distinct horizontal and vertical zonal sequences of alteration minerals in the intrusion and adjacent rock. These zones may be grouped into different mineral assemblages based on model abundances and the types of minerals present. Lateral zonation, porphyritic alteration zone. This is the outermost alteration zone and is widespread, 300 meters up to 10 kilometers. It is always present and is composed of chlorite, epidote, carbonate, and pyrite. This alteration type forms by conversion of the mafic minerals hornblende, biotite, and pyroxene to chlorite, epidote, and plagioclase, going to epidote, carbonate, and or recrystallizing to albite. Argillic alteration zone. This is an area of clay alteration and is most extensive in rocks rich in plagioclase feldspar. It is not always present. Prominent minerals are kaolinite and montmorillonite, both of which replaces plagioclase. Pyrite is always present. When it occurs, this alteration zone is typically narrow and lens-like. Lateral zonation, sericitic or phylic alteration zone. Sericite, quartz, and pyrite are the dominant minerals in this zone, accompanied by minor amounts of rutile, chlorite, and ilmenite. Significant amounts of ore are associated with this alteration type, with the ore minerals dominated by chalcopyrite with or without molybdenite and gold. Potassic alteration zone. This is an inner or core zone characterized by potassium feldspar and or biotite with or without amphibole, magnetite, anhydrite, and fluorite. Associated ore minerals may be chalcopyrite, bornite, chalcocite, molybdenite, and gold. Pyrite is usually a minor constituent. Vertical alteration. Porphyric copper deposits also exhibit a vertical zonation of alteration minerals that is distinct from the lateral zonation assemblages. Vertical alteration zones are not common at porphyric copper deposits because, number 1, most of the overlying rocks have been eroded away. Number 2, they will only form where there has been little interaction between the hydrothermal fluid and groundwater. The alteration assemblages and zonation associated with this alteration were determined by deep drilling in recent volcanic terrains and partial preservation at more recent discoveries, particularly those in active island arc environments. The vertical alteration has been subdivided into 3 zones, which are referred to as felsic A, P, and K. Vertical alteration. Overall, felsic alteration represents extreme base leaching from all aluminum phases in the rocks except for aluminum itself. This alteration type forms from acidic fluids. Felsic A. This is a high temperature, greater than 425 degrees centigrade alteration, represented by extreme leaching of the rock. Minerals present are andesite, corundum, and quartz, with or without pyrite and chalcocite. This alteration occurs immediately above the host intrusion. Felsic P. This alteration type forms at moderate temperature 300 to 425 degrees centigrade, with the minerals present being porphyrite, diaspore, topaz, and quartz. Felsic K. This is a low temperature 100 to 300 degrees centigrade alteration with the representative minerals being kaolinite and quartz. This zone may extend all the way to the surface where it is represented by hot springs and a steaming ground. In the near surface environment, other minerals commonly present are alunite, hematite, and a diaspore. This zone may not be present. Host rocks. Common characteristics. Number 1. Associated igneous intrusive rocks range in composition from diorite and quartz diorite to granodiorite and quartz monzonite. Some are alkalic and include monzonite and cyanite porphyries. The intrusions are typically cylindrical stalks or broad, domal-shaped, near-surface intrusions. Number 2. Multiphase intrusive events or phases are common and range from 2 to 3 to more than 14. There are 7 at Bingham. Host to or is often the most differentiated and youngest phase present. Number 3. One or more intrusive phases is porphyritic. Sometimes all phases are porphyries. Phenocrysts range from 30 to 55%. Another phase present is an aplitic rock, one with a fine-grained sugary texture caused by pressure quenching of the porphyry due to rapid ascent and volatile loss. At depth, these porphyritic intrusions merge into the same underlying magma chamber. Number 4. Plagioclase is always present with hornblende, common in rocks of intermediate composition and biotite. Potassium feldspar and quartz common in more silicic rocks. Rocks containing plagioclase, potassium feldspar, quartz, biotite, and or hornblende formed at 675 to 700 degrees centigrade with more than 4% water in the magma. In alkalic intrusions, the minerals typically present are plagioclase, sodic-rich clinopyroxene, leucite, and garnet. Accessory minerals may include apatite, zircon, magnetite, titanite, fluorite, and monzite. Number 5. Breccia, pipes, diastreams are common and they may represent hydrothermal explosions caused by rapid fluid rise and, in the near surface, rapid expansion. This causes rocks to fracture and break and may also lead to the flashing of water to steam leading to phreatic explosions. All rocks have been extensively altered. Number 7. Veins in the rocks are ubiquitous. They form throughout the life of the porphyry magmatic hydrothermal system, as do breccias. Veins contain a large percentage of the ore minerals and represent the locus of greatest fluid transport. Number 8. Bottoms of porphyry deposits, areas below the ore deposit, are regions of abundant quartz veins, porphyry dikes, and a widespread alteration that may include calcic, garnet, pyroxene, epidote, skarn on the flanks of some system, and reasons coarse-grained aggregate of muscovite quartz, which occurs directly beneath the ore southwest USA. Ore geometry. Igneous host rocks constitute the central core of the ore body, or all of it, or may then extend outwards for a variety of distances into the country or wall rocks. Distribution of the ore is based on number one, composition of all rocks, number two, degree of fracturing and faulting. Because most intrusions are steep-walled cylinders, there is a strong tendency for the deposits to exhibit a concentric or shell-like pattern of sulfide and alteration minerals. At first inspection, the mineralization appears to be widely disseminated, gives the rock a salt and pepper look. However, on a microscopic scale, it can be seen that most sulfide minerals are actually located along networks of microfractures, stoneworks. This small-scale fracturing only extends outwards as far as the sulfide alteration assemblages and is believed to be due to first boiling of the hydrothermal fluid. The mineralization tends to exhibit an inverted cup shape with a low-grade core composed of minor chalcopyrite, often accompanied by molybdenite and gold, bornite and chalcocite, may be present in minor amounts. This zone has low amounts of pyrite. B. The main ore zone composed of chalcopyrite 1 to 4% and gold with or without silver. Bornite and chalcocite are absent and there are trace amounts of arsenopyrite and cassiterite. C. A pyrite-rich shell 10 to 20% with minor chalcopyrite 0.1 to 1% grades outwards into a low pyrite shell 2 to 5% with traces of chalcopyrite. May get veins of galena, safflarite, and silver minerals in this zone. Types of porphyritic copper deposits. A. Quartz diorite type. Number 1. Host rocks are diorite, quartz diorite, syenite, and monzonite. 2. The rocks have low silica-alkali ratios. Number 3. There is little or no free quartz. Number 4. Magnetite is a common accessory mineral. Number 5. Hydrothermal alteration, potassic, biotite-rich, greater than porphyritic, or potassic is greater than argillic to porphyritic. Number 6. These deposits have high gold and a low molybdenum. B. Quartz monzonite type. Classic Southwest United States. Number 1. Host rocks are quartz monzonite, granodiorite, and quartz diorite. 2. The rocks have high silica-alkali ratios. 3. There is lots of free quartz. 4. Little or no magnetite, low gold contents, but they have more silver and are enriched in molybdenum. 5th, hydrothermal alteration is potassic to sericitic to argillic to porphyritic. Tectonic settings. Type A is associated with island oaks, deposits common in Australia and around the Pacific. Type B is associated with continental margins and represented by deposits in the Andes Mountains, southwest USA, and British Columbia. Formation. Number 1. Porphyritic copper deposits form in active volcanic environments, with the intrusions feeders for volcanic activity at the surface. 2. They are associated with hot springs and epithermal gold deposits, which occur in the upper zones of the vertical alteration. If subaqueous may be not springs with associated volcanogenic massive sulfide deposits. 3. Evidence for their genesis comes from isotopes, fluid inclusions, and economic petrological studies. These show that the hydrothermal fluid was in equilibrium with the potassic alteration assemblage which formed at 500 to 750 degrees centigrade and is indistinct from magmatic water. 4. The hydrothermal fluid from fluid inclusion studies was up to 60% NaCl. It underwent boiling and was high in copper, iron, and sulfur. Number 5. Potassium silicate alteration assemblages and associated ore minerals formed from high temperature acidic magmatic brines. Number 6. Isotopes and fluid inclusion show that sericitic alteration assemblages formed from mixing of magmatic fluid with groundwater. The temperature of formation was 300 to 600 degrees centigrade. The pH of the fluid has increased and the salinity decreased. Also, K by H ratios had decreased. 7. Porphyritic alteration formed from a highly diluted low temperature 200 degrees centigrade neutral pH fluid that was less than 5% NaCl. It has low K by H ratios. 8. Vertical alteration potassic is greater than advanced argillic is greater than quartz is indicative of a boiling magmatic fluid cooling as it rises toward the surface. Temperatures range from 700 to 3000 degrees centigrade. pH is low and the K by H ratios are high. There is little mixing with groundwater. Porphyry molybdenite deposits. Similar to porphyry copper deposits in style, alteration, grade, and size. Differences: A. The ore is dominantly molybdenum MOS2 0.1 to 0.4% with associated tin, tungsten, and REEs. B. The host rocks are granites, granite porphyries, granodiorite. They are more felsic than the intrusions that host porphyry copper deposits and thus are believed to have been derived from more evolved magmas. C. To get more evolved magmas, thick continental crust is needed. Need long residence time, which infers a stable upper crust and also long-lived magma chambers. D. The deposits are associated with continental rifts. There is one major and one minor type of porphyry molybdenum deposit. Major climax type and includes Henderson, Cuesta, Mount Emmons, etc. Minor quartz hill type includes Endako. Climax Henderson type multiple intrusions of applied porphyry, granite porphyry, intrusion associated with overlapping shells of alteration and mineralization. Intrusions are alkali-rich, meta-aluminous, high silica rhyolites. Top part of the intrusions is characterized by intense silicification with associated topaz, wolframite, fluorine-rich mica, fluorine-rich garnet. Quartz hill type. Similar to Climax Henderson, but less molybdenite and a lower enrichment of niobium, zirconium, rubidium, fluorine, tin, and tungsten. Host rocks are granite porphyries with biotite, granodiorite intrusions also in the area. Niobium is 150 to 200 parts per million and rubidium is 500 to 1000 ppm. This compares to 20 to 100 ppm niobium and 150 to 400 ppm rubidium for porphyry coppers, which represents less evolved magma and shorter crustal residential times. Porphyry gold. Many porphyry copper deposits, especially in the diorite quartz and the diorite class, are major producers of byproduct gold and silver. The gold, with or without silver, may occur in centrally located stockworks with the copper plus minus molybdenum. Proximal in calcic skarns with copper. About 20 porphyry deposits in Western world contain greater than 0.4 gram per ton of gold, 0.12 Oz per ton. Porphyry molybdenum deposits. Bingham, which has produced 23.4 million ounces, is a major U.S. gold producer. OKTD has 0.07 Oz per ton. In alkali porphyry copper gold deposits, the gold is in stockworks. The deposits have potassic alteration with anomalous a million ton up to 8%. Copper minerals are chalcopyrite and chalcocite. Thank you so much.